Today we have Michele joining us from the Swansea Academy of Advanced Computing, and he's going to talk to us about aspects of machine learning.
Okay, so thank you for the introduction. So yeah, so basically this talk, this presentation is about some aspects of machine learning that I came into. I've encountered by studying some things on my own, trying to do some self-learning and self-teaching, and so I wanted just to say that this is a talk by me, which I'm not an expert on the subject, and I think that in this room already I see people which, in my opinion, are more expert than me on that. But well, I wanted to learn more about this subject. I think that there is a general interest about this, so I wanted to share what I know about this, and if possible, I would like to learn about from other people, or also get some ideas on how to learn more about the subject in general. So without further ado, we'll go a bit further. So the outline, I think that if I want to explain or to define what machine learning is, I think I should basically follow this outline, which is say a bit what machine learning is, so what flavors of machine learning do exist. I think this is possibly an arbitrary classification between supervised, unsupervised, and reinforcement, but well, that's what I found in some courses and books, so that's what I'm going to stick to. Then some general principles in machine learning. This is, in my opinion, quite interesting because when I wanted to learn about machine learning and look for tutorials on the internet, basically I was finding mostly some practical, some tutorials, some practical advice, but nothing that would somehow guide the understanding of it in a more general and possibly scientific or logical way. And then, just to give a bit of context, I will talk about the examples of problems and techniques in machine learning that I have come across, and then I will give a bit of historical perspective, and I will mention the resources that I used to learn about this. So, well, this is going to be very introductory and very basic. I think I will try to go quite fast, and if there's anything that is not clear or anything that is wrong, please stop me. So, flavors of machine learning. So, I think, from what I've learned, machine learning can be divided into basically three big areas. Supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, the task is basically to approximate the function, which can be seen as, classification problems can be also seen as function approximation in some sense. Okay, and well, the input is labeled data or function values, and the output is the function or a classifier, which will perform the task of classification. And the idea is that we want to generalize from the labeled data to the data we have to some examples, to some instances that we don't have, and we would like to, this is called induction, right? So we want to generalize from what we know to something that we don't know. In unsupervised learning, we don't have labeled data, okay? And the point, the aim is to describe data, okay? So we need to, we want to get a description of the data, and this actually boils down to some optimization problem, actually. So here we have a goal function, which describes, our, which is related to what we want to achieve. And well, out of this kind of algorithms, we get data description and maybe also some representation of the data in a sense of compression, for example. And well, then the third area, the third flavor of machine learning is reinforcement learning, okay, which is mostly about finding optimal behaviors. Let's say that we have like a game, okay? So we want to learn how to play a game, and basically we need to feed the algorithm and the model and some short-term rewards, okay? And this information is hidden, is not directly available. The agent or the learner must learn it himself, and the output of this procedure is to get the behavior best agent, best policy, which will maximize the long-term rewards. So, some general principles. I think that this is mostly related to supervised learning, I would say, because it is mostly. So basically, when we want to learn a function or classifier, we need to define where are we looking for the function, where are we looking for among which kind of hypothesis we are. So there's basically an hypothesis space, okay, which is defined basically by what can be called a restriction bias, okay, which tells us, basically it's a definition of the hypothesis space. Where if you have a bigger space, then we restrict it to some, for example, well, there are some examples of this. If we want, we can actually go into that. But there's not only restriction bias taken into account, so basically saying which hypotheses are possible and which are not possible, the one that we can consider, the one we will not consider. But also there's some preference bias which we can take into account. So for example, the fact that some hypotheses will be more probable a priori. Okay? Another idea, another concept that we need to take into account is the so-called curse of dimensionality. So for example, if we want to learn classification, to do classification on some data space which have a lot of dimensions, it would be very hard to do that, because of course the number of possible concepts, or the number of possible, the hypothesis space increases exponentially with dimension, the extent of the hypothesis. And another thing which I would like to remark is that it's quite possible, quite easy to see that bias-free machine learning is futile, I think. This is a possibly quite theoretical concept that if someone has some ideas on, I would like to discuss more maybe. What I mean is that bias is, what I want to say with this slide is that bias is really important, and it's a guiding principle in towards the kind of solution we want to get. And and we cannot do away with it, basically. And so there are other ideas that can be important. So, for example, that let's say, I collected just a bunch of concepts that in my opinion are quite important. For example, data quality and quantity. Okay, and just a word on that. Mostly a learner, so an algorithm that learns, has some performance which can be measured mostly. The most important thing is the quantity of data that is needed to learn, and not too much about the computational complexity that is that we are used to think about when we think about arguments in a more computational sense. That's it. I don't know. Other things, a phenomenon to take into account is the so-called overfitting. And overfitting is means loss of generalization when we train, when we use all the for example, in neural networks, when we train for too long, we have overfitting. This is a phenomenon that happens, for example, even with decision trees. Okay, and basically we have loss of generalization, and we basically believe in the data that we have too much, and so this is something that we need to take care of usually, and there's some techniques that helps in this, but it's an important thing. There. So, okay, let's move on, because anyway, this is just to show something that we can talk about later. So, so just a quick reminder what the Bayes theorem is. We don't know if everybody's yeah, I would say so. Okay, so basically a guiding principle to look for hypothesis, so to look for classifier, is basically to find to maximize this a posteriori probability. Okay, so over there, okay. And this has, I mean, in my opinion, this is somehow in, a guiding principle that we can see later on. Even for those algorithms which don't take into account probabilities directly. So an interesting concept, in my opinion, to talk about is the so-called Bayes optimal classifier, which doesn't use only the hypothesis, which is the maximum, which is the most probable a posteriori, but also basically it uses all the hypotheses, and then basically the classification that is given is basically the one that comes from this computation. So we sum over all the hypotheses, and basically this is the probability of the hypothesis J given the data, and this is the probability of the classification given that hypothesis. And yeah, so this is hard. Using this is pretty complex because we need to evaluate all the hypotheses basically. So, but it's somehow interesting. So let's move on. So I will go now quite fast through examples in supervised learning. Some techniques which are used. So decision trees. Okay. So here's an example. We have a concept, a function that we want to approximate or to learn, which is basically this outcome here. So we have some weather conditions, the outlook, temperature, humidity, and wind, okay, and we want to define, we want to learn what is the outcome, okay, if we are going to play tennis or not, okay? This is and basically, we can do this with a decision tree, okay? So the idea is to ask one question at a time. So for example, we have the outlook, okay? We can ask what is the outlook going to be like. And for example, if you look at this table, it turns out that if it's overcast, we are always going to play tennis, yeah? And if in case it's sunny or rain, we need to ask other questions. And we can build this kind of decision trees by looking at, by using some algorithms. For example, ID3 is one, okay? There are, of course, there are many others. And but this is the one I learned about. And it's a greedy algorithm that basically chooses to ask the questions that give the largest information gain first. Yeah, there are all the other choices of information gain possible, but well, this is one. Okay. This table actually comes from the book from by Tom Michele, machine learning. So another example is neural networks. Okay, so this is another technique that we can use to solve to learn concepts. Okay, and it's based on the so-called perception, which is this. Okay, so it's really simple, really simple idea. I mean, at least the basic. So we have a set of values which are fed into this neuron, and the output is computed in this way. Basically, we take a linear combination of the inputs, we subtract a threshold, and then, well, we define what to do with this. So, there are several options. The original one, the perception by Rosenblatt in 1958 or 57, was just to use a sigma function. So a function would be 0 if the argument is 0 and 1 if the argument is positive. Okay. There are other versions of that which have different implications, both from the computational point of view and both from the learning from the result. And there are several techniques that are somehow related to that. And we can actually, when we want to use neural networks, basically the idea is to take several units of this kind and link them in a way that is depicted a bit like that. Here, it's the idea is that different layers of neurons communicate to the next, okay? And always to the next. There's no feedback loop. Okay? This kind of neural networks are used, for example, in image recognition or even reinforcement learning problems, I think. And basically, here, in the case of classification, for example, if we need to distinguish between 3 categories, we have 3 neurons at the last layer, okay? And each of them will output a probability, okay, of the pixels representing a cat, bridge, or chair, for example. Okay, and what we usually do is to minimize the cross entropy between this prediction on many images and data and the labels, the correctly labeled data. Can we talk about this later? And so, go on. So another supervisor learning techniques that's quite used is the so-called k-nearest neighbors, where we basically, let's say that we are in a space which is here, that is represented as 2-dimensional, okay, and we have clusters which are being labeled. So data which different color have different labels, and we can use this technique to assign this unknown new data to 2 clusters. And the technique that here is described is basically to take the nearest k instances to the for example, this unknown point here, okay, and see basically the maximum. I mean, which cluster, which class has the maximum representatives among this this set of k instances, and then assign the point, the new data to that. Okay, and I want to say, for example, that if we can take k equal to 1, for example, this point would be assigned to the orange class. But if we take, for example, 3, okay, it will be assigned to the green. Okay, so that's something to take into account. There are several variations possible about this. It's also possible to apply this to non-metric spaces. Okay. I don't know exactly what are how this technique is used in industrial contexts, but for sure in research, I think there's some research going on about this. Another technique which was really famous in the 90s, because as far as I've read, for example, that in the 90s this approach, support vector machine, was almost as good as neural networks for image recognition, in particular for handwriting recognition. Yeah, so basically the idea is that we wanted to separate some instances, to do classification in a metric space, okay? And yeah, so here if our data is linearly separable, that is, we can actually draw a line, a straight line that separates the two classes in this case, okay? Well, we can just get this straight line and define and basically predict if an instance fall in one category or the other. Okay? Using this simple separation. I think it's quite easy to understand. I think that mathematically boils down to a quadratic programming problem. Okay? Basically, we need to minimize the square, the norm of this vector, which is a vector which is perpendicular to that line, okay? Under this constraint, okay, where x is the position, represents the position of the instance, okay, and y instead is the label, so it's the one or names one, okay. Makes sense. This problem can be remapped into another problem, and here I think in this way, when the problem is written in this way, so basically we need to maximize this with subject to these constraints here. It's quite clear that we can do here. I mean the vanilla version would have, in place of this kernel, the linear kernel. Okay, so just the scalar product between these two vectors, x and y, xi and xj. We can actually generalize this and use another kind of kernel. For example, a famous one is this called radial basis function kernel, which is defined like this. And when can that be useful? For example, when our data is not linearly separable, maybe, for example, if you have that, the plus point are all close to the origin, and instead the minus point are far away from the origin, and we want to basically separate the two categories this way, we can actually use the kernel trick and separate them. The name is a bit strange, because why it's called support vector machines. I think this is due to the fact that when you run this minimization problem, okay, most of these alphas will be basically 0, okay, and only a handful of them will be different from that. In this particular case, it's pretty, it's very apparent that only these 3 points count in the definition of what this, or where this line, the straight line is. So it's the position and the orientation of that. So that's why these vectors, these three vectors, are the support of this. I don't know exactly why, but I mean this made sense. So okay, going on. There are other classifiers which I don't have time to talk about, and we can actually have a chat later. I keep saying that, but because I really want to. So logistic regression, okay, is another possible classifier that it's quite, I think that used really with profit. And there's also a multinomial version of it, but let's stick for the moment to the binomial version. So where you have only two categories. Okay, if we define P as the probability of being in the plus cluster, then we can make this assumption. That is basically that the logit, it's called this thing here is called the logit of P, has this form. Okay, and yeah, and we can actually estimate then W or W and B using the maximum likelihood method, which is basically what we're talking about in one of the first slides. Then there are some other techniques which are called ensemble learning. Okay? Basically, we have in these techniques we train some so-called weak learners on subsets of data. Okay? Weak learners are basically algorithms that classify data with a probability at least 50% correctness, so more than 50% correctness. So basically, they are just better than tossing a coin. Okay, if they are consistently better than that, okay, we can actually combine them to obtain a better estimator, better classifier. Okay, this is the case in boosting. I don't remember exactly in bugging. Bugging is similar, but I think the boosting is a bit more refined. I've heard saying that boosting overfits, and I also heard claims that instead boosting does not overfit unless the learners that we use overfit. So I don't know. I have no practical experience on that, as it's already clear, I think. And so, an example of mixing this ensemble learning and what we were talking about, I think we were talking about these decision trees, is the random forest approach. Basically, the weak learners here are decision trees, and we have many of them, and then we make them vote, and we take a random forest classifier. About unsupervised, moving on to unsupervised learning, a problem in unsupervised learning is clustering. So, these are possible ways of solving clustering problems. Okay? So, the most stupid, I don't know if it's stupid, but the simplest algorithm that I encountered was the so-called single linkage clustering. So we assign, if you have a case of 5 minutes, I think it's quite easy to figure out, to imagine what I'm talking about. But, well, so let's say that, how to present this better? Well, there are several variations of these algorithms. I would say we can talk about this later if you want. And moving on, another task in unsupervised learning, which is quite interesting in my opinion, is the so-called feature selection transformation. This is something that can be really useful in conjunction with the classifier. So the problem that I was stating before, something I mentioned before, is the so-called curse of dimensionality. So if our data has a lot of dimension, a lot of feature, we may want to actually get rid of some of them in order to make the classification, the learning easier. And we can actually use some techniques to choose or transform features so that so that what I just said is possible. And I was just to mention some algorithms to do that. Okay, for example, one of the possible techniques is the so-called principal component analysis. Okay, which is as far as I know, a linear transformation. So, for example, here we have a very simple example where actually our data has just two features, x and y, okay? And we want to like get rid of one of those numbers. And one way is to use using PCA means that basically we look at all the data, okay? And we basically diagonalize the correlation matrix and take components with the highest variance. So basically we just take this. And if we want to just get rid of one of the two variables. Another thing which I'm not going to dive into because actually could be the subject of the next talk, the next seminar, okay, is autoencoders. In here, there's a depiction of that. I mean, this is actually a neural network, and the idea here, as in the principal component analysis, in some sense, is to try to reduce the amount of data that we need to represent some input, okay? But reducing minimizing the reconstruction errors. Yeah, in the case of PCA, for example, we want to minimize the L2 norm of the error. And another thing which is, to me, is really intriguing, and really like to learn more about, is the so-called independent component analysis, which is not PCA. Okay, it can be linear or non-linear. I've just seen linear examples, but I've heard that there are also non-linear possibilities. And well, basically, just to make a better example. So, for example, let's imagine that we have a hidden source, okay, which has basically two features, okay, and basically the visible signal will be a linear, basically an affine, in this case, affine transformation of the hidden source signal. Okay, if we run PCA on this, we will get this. Okay, basically, so we will find the principal axis. Instead, if we run an ICA algorithm on that, we would hopefully recover the same uncorrelated, the same independent inputs as before, and as the hidden source. And the possible application of this is the so-called cocktail party problem, okay, where we have different people speaking at the same time, okay, and we have different microphones, and we would like to basically obtain the voices of the single individuals, or the individuals separated from actually the signals that we have here, which actually are a superposition of the voices of the hidden sources. Okay. Going on. So I will move into reinforcement learning. There are some omissions in this, but it's already I would say quite big. So I will motivate my omissions later. So moving to reinforcement later, reinforcement learning. I would like to define a bit more precisely what it is, and so in order to do so, I will just define briefly what a Markov decision process is. Basically, we have a universe, okay, or a system which can be in different states. Okay, in this case, the state can be the position of an agent that needs to hop around the map. Yeah, and this agent is going to take actions A, which will hopefully change depending on the model. Okay, they will change the state. So, for example, we are in state S. We take action A, and we end up in state S prime. Okay, and this model is stochastic. So actually, these are transition probabilities. Okay, so we don't actually. It's not true that we always get what we want, and well. The important thing is that we have short-term rewards, okay, which actually should be okay, or S. This should be an S. So a reward for being in a state at a certain period, point in time. There are other formulations. The other formulation of reward, which now we are not concerned about, and. The idea is that we want to find out what are the best actions in Java, so that we maximize the value, okay, of a state, okay, which is defined in this recursive way. Okay. Now this is called the Bannon equation, and well, the max here stays to is here to basically tell us that we want to make choices to maximize this quantity here, and gamma is a discount factor which is I mean, hypothetically I would set it to 1. I mean, I would like to set it to 1, but I think that in some mathematical derivation, it's important that this gamma is not 1. Because, for example, if gamma is not 1, you cannot prove the convergence of some algorithms. Okay. And so, well, these problems, in some sense, the Markov decision process problem boils down finding the best policy, okay, which is defined in this way. That will maximize the long-term rewards. In reinforcement learning, though, we actually want to the agent to also learn the model T, okay, the so-called model T, or maybe not exactly T. Maybe it can the agent can learn V directly, or even pi, even the policy. There are different versions of that. A possible approach on this, which has been used with success in some, for example, in playing games, in creating agents that play games with very high level of skills, is the so-called TD lambda algorithm, which is a sort of Q-learning thing. I mean, it does. I mean, I need to there should be some difference in these terms, but why? I mean, while I was looking into this, I couldn't find. I think that they are highly related, and yeah. So this is more or less the problem. What the problem is about, and there are other possible complications. For example, that the state of the system could be not observable, could be not, yeah, so there can be some hidden variables, some hidden features of the system that the agent is not automatically aware of, and it's something that must be taken into account. Okay, so moving on. Another kind of problem in reinforcement learning which is totally it's basically the opposite of a deterministic macro decision process, is instead this other problem, which is the so-called k-armed bandit problem. Basically, these are slot machines, okay, which have a different probability of giving us a reward, okay, of giving us. And we don't know which one of these machines is the best, okay, and. The problem here is to try to maximize the reward, long-term rewards, or even the reward in a finite horizon time. Okay, and there's a competition between the idea of exploiting what we know. So, for example, we try. Just sometimes, we do five attempts and we get an estimate of the probabilities for each machine, and we stick with one that has a higher probability of giving us a reward. Or maybe we can explore further for more time. And this is an example of the so-called exploration versus exploitation problem. Okay, and in this particular case, the so-called, exactly this one, there is a solution which gives us the best action to a specific moment, which is so-called the keys index. And basically the keys index, if I'm not wrong, is an estimate of how big should be. I mean, if we have a keys index for each arm, okay, sure. And basically, this represents the reward that we should have, that we should get from another arm, so that we could choose it instead of keeping using the one that is that we're considering. So, well, anyway, this is not something that can be generalized to other problems, but I think it's worth mentioning that this problem is somehow solved ultimately in the literature. So, things worth mentioning, but I don't have time to discuss. And so, genetic algorithms, okay, which are kind of unsupervised learning. And for example, one flavor of genetic algorithms is genetic programming, which would be interesting for, we were talking about it yesterday or 2 days ago. Maybe it would be cool to have a genetic programming algorithm to do some optimization on assembly code, maybe. I think that people have done it already, and it would be nice to learn more about it. Then another topic that I didn't mention is Bayesian networks and naive Bayes classifier, which is, I think, used very efficiently by Google to do text classification. And there are, of course, other flavors, other aspects of reinforcement learning, which I didn't go through. And yeah, of course, there are other things to which can be oblivious to, given my lack of knowledge. So a bit of historical perspective, just to say that even if machine learning got very fashionable recently, it has been for a long time in the air. And these are some dates of the birth dates of some techniques I've been mentioning. And as you see, these are not recent, or recent if you want. Yeah, they are recent, but not in the last 10 years. And also considering, neural networks and deep learning has a possibly more shorter timeline than machine learning in general. Okay, but I think it's worth mentioning that for some, I mean, at least for some interpretation, for some reading of deep learning history, there have been some moments of enthusiasm and some winters, so-called. This is the way Jan defines them. And yeah, I mean, the perception is something that dates back to 1957, and there were even some precursor of it during the Second World War. People came up with this idea pretty early. And then in 1969, it was proven that the perception was not able to represent XOR, the XOR operation, and that then if you want to, in order to represent that function, we would have to use multiple layers of perceptions, but then it was really hard to train them, because there was no, people didn't have clear in mind some ideas that came later. And then there was another spring later on in the 80s, which was basically due to the fact that the backpropagation algorithm to train neural networks was discovered. Okay, but if I remember correctly, this algorithm was actually first mentioned in a PhD thesis, I guess, in 1975, and the paper on it was published only in 1982, because back then there was no enthusiasm at all about these things. And yeah. So there was a second flourishing of neural networks and deep learning. I don't know if deep learning is a term that was created later to basically rebrand neural networks, and and basically between 1986 and 1997 there was another spring, which was based on the fact that finally multi-layer neural networks became trainable, and backpropagation was somehow understood, but there were other problems which were related to the fact that anyway the backpropagation algorithm was quite heavy at the time, but anyway there were some problems which later on were solved. Okay, and basically we are now in this era of where everybody's talking about deep learning, and deep learning actually is a term that was created after 2000 to rebrand neural networks which were possibly seen as not competitive with other, methods, or that were not delivering on the promises that the people thought they would deliver on. And well, given that, I'm almost finished. I wanted just to see, I mentioned some results. So I think that recently it's good. It's good to mention that deep learning is actually good at doing some things. For example, image recognition. And if I am correct, this is something that I were just before coming here, because so basically in this image recognition challenge, which is ImageNet, which is a database of images, labeled images, which is around 22 million of images, categorized in like 15 million images categorized in 22,000 categories by human workers at the so-called Amazon Mechanical Turk facility. It's a service that Amazon provides. If you need some human intelligence, you can actually hire them and they can do this for you. It's possibly the path to AI. You need to fake it until you make it. Well, anyway, this competition in the last 8 years has shown very, very nice advancements, and I think that at the beginning the error rate was, the error rate has gone down consistently, and yeah, so I think that for the 2018 version they are going to make it a bit harder. So for example, instead of images, they want to introduce a contest for recognizing for classification of 3D data instead. And another impressive sort of result is more in the realm of reinforcement learning. So for example, consider self-driving vehicles. Yeah, I think that the turning point was between 2004 and 2005. Basically, only in 2004, only one participant completed the challenge, which was just driving like order of 10 miles in the desert or something, I guess. And in 2005, there was basically a sort of step function, and a lot of teams managed to get better than the winner of the previous year. And so maybe that's when things started getting hot again. Anyway, it's somehow funny to me that these self-driving vehicles not so, there were earlier example of that. For example, in 1989, okay, in the middle of the second spring of AI, okay, they managed to do this, which was basically yeah, they were using neural networks. Actually, the first layer was like 30 times 32 pixels, and this was running on a it's less than 1 gigaflop processor, and so I cannot say. I imagine that this didn't work out too well eventually, but I can't say I can't say the reason. I guess that possibly it was not as reliable as you would like a car to be nowadays. But anyway, it's somehow impressive. And with this, I just want to say that machine learning and deep learning have a long history. Deep learning, the term itself not, but its roots are somehow long in the past. And that's it. These are the resources that I based myself, I tried to learn from, with not so great results, you may say. And yeah, so maybe you can share them. I found them useful somehow. And let's say this is just this. I think this is a bit more than the thing that you can find on Google. Just looking for the typing machine learning. So it's a bit more. I think that there can be some value in what I put here. Just that. I forgot to add thank you for your attention slide at the end. So thank you. But I thank you for your attention.